Here is the lesson video for section 19.1, Acid and Base Theories. We're starting a new chapter, chapter 19, and we're going to investigate some substances that we've used a lot in our labs and that we've discussed earlier this year as far as how to name them, how to write the formulas for these. The substances are acids and bases. Learning goals are to contrast three theories about acids and bases from three different scientists. One scientist's last name is Arrhenius. Then there's a pair of scientists that work together on a second theory. Their last names were Bronsted and Lowry. And a third scientist is Lewis. So let's look at that learning goal and examine the theories from these different scientists. Chemicals called acids and others called bases have been frequent reagents in our experiments this year. We've used weak acids and bases and strong acids and bases. We've used low concentrations. For example, the molarity may have been 0.1 molar. And we've also used high concentrations. For example, 6 molar. Some of these chemicals are in foods we eat, and some are critical to processes that support life. Others have important industrial and medical uses. So acids and bases are really important chemicals. Lots of uses, they're all around, but what are acids and bases? Let's look at some different definitions of acids and bases from three different scientists. First, we'll look at Arrhenius acids and bases, because this is the understanding of acids and bases that we've already used earlier this year. In 1887, Swedish scientist Svante Arrhenius proposed the following explanation for the properties of substances called acids and bases. The Arrhenius definition of an acid is, an acid is a compound that produces hydrogen ions when dissolved in water. A base, according to Arrhenius, is a compound that produces hydroxide ions when dissolved in water. And like I mentioned earlier this year, whenever we've talked about acids or bases, we have used the Arrhenius definition of those terms. The chart on the left gives some common acids. HCl, hydrochloric acid. We've used that in a lot of our labs. H2CO3, carbonic acid. HNO2 is nitrous acid. HNO3 is nitric acid. That's one we've used in labs. H2SO3, sulfurous acid. H2SO4, sulfuric acid. We've used that in labs. And CH3COOH, that's acetic acid, which is the acid that's in vinegar. You'll notice right away in the names of these different acids that all three of the acid naming rules are represented. HCl is hydrochloric acid. The H2CO3 is carbonic acid, so the acid that ends in ic. And HNO2 is nitrous acid, an acid that ends in OUS. Now on the right side, the chart is showing some common bases. LiOH is lithium hydroxide. NaOH is sodium hydroxide. We've used that one in our labs. KOH is potassium hydroxide. CaOH2 is calcium hydroxide. And then you see some more. You'll notice right away in the chart on the right, all of the bases contain hydroxide. That's the Arrhenius definition of a base, a substance that contains hydroxide, and if it's dissolved in water, will dissociate and release hydroxide ions into the water. On the left side, all of these acids that you see are acids according to the Arrhenius definition. They all contain hydrogen. If they are dissolved in water, they will dissociate and hydrogen ions will be released into the water. Next, check for understanding. Write a dissociation equation to show that H2SO4 aqueous is an Arrhenius acid. I'll pause the video for you to try this, and then also try number 2 and number 3. Here's the answer to number 1. On the left side of the arrows, I've written H2SO4 aqueous, and then on the right side, shown which ions it dissociates into. It will make hydrogen positive ions and then sulfate ions. Sulfate had a -2 charge. To balance the equation, you notice the red 2 in front of the hydrogen. Now here comes the answer for number 2. On the left side of the arrows is the NaOH compound, and then on the right side are the ions that it dissociates into. Continuing on, the dissociation equations written above can be written in another form to more clearly show that water is involved when ionic compounds are called acids and bases. This example is the same as this equation that we wrote up above. You'll notice that up here up above, it says H2SO4 aqueous. Aqueous means there's water involved. And so down here, we've just explicitly identified that water's involved by writing water as one of the reactants. Then on the right side of the arrow, up above, you'll notice it says H+ aqueous. That means that there's hydrogen ions dissolved in water. But let's think about that a little bit deeper. What does it mean to have a hydrogen ion dissolved in water? That means that there is an H2O molecule attracted to a positively charged hydrogen ion. That's actually H3O positive. And look up here, SO4 -2, but we said aqueous after it. Let's think, what does that mean to say aqueous? It means that that SO4 -2 ion has been dissolved in water. Well, we learned about dissolving in water. We know that that means a water molecule gets close to that ion, that there's an attraction between the positive side of the water and this negative ion. The water molecule floats away and takes the ion with it. So we could write HSO4 negative. It's just an alternative way of saying the same thing we did up above when we said SO4 -2 aqueous. The reason this is only now a -1 because there's a hydrogen with it. Hydrogen is +1, which cancels away one of the negatives on the SO4. And now the overall charge of this only goes to the -1 power, not the -2 power. The H3O positive symbol is the hydronium ion. The reason that it would be common to write it like this is because hydrogen ions don't exist freely in water. The negative side of the polar water molecule is going to attract the positively charged hydrogen ion. So it's more accurate to write equations that involve hydrogen ions in water by writing H3O positive instead of writing H positive aqueous. You might also realize that an H positive ion is simply a proton. A hydrogen atom, a neutral hydrogen atom, has one proton in the center and one electron revolving around. But if it loses that one electron to become an H positive ion, then what remains? Just a proton. I mean, hydrogen doesn't even have any neutrons in the center. It just has a proton. So every time this year when we've been writing H positive ions, we're really just saying a proton. Next, let's look at some general properties of acids. Acids are electrolytic. That means they can conduct electricity. This is a word that we had in our earlier chapter this year. Acids cause indicator dyes to change color. Acids taste sour. Now, some acids you wouldn't want to test that with because the acid could be so dangerous to you that if you ingested it, it would be very dangerous. But some acids that are edible, if you were to taste them, they would taste sour. For example, citric acid. Right? Citric acid is in citrus fruit. Citric acid is added to foods to give it a sour taste. Acids are caustic. That means that they burn body tissues, your skin or your eyes. Acids produce hydrogen gas when combined with metals. We did a lab earlier this year where you had a test tube, you filled it up maybe half full with hydrochloric acid, and then dropped in some pieces of metal like copper and magnesium just to see what would happen. And it bubbled and fizzed. That was hydrogen gas being produced. Next, let's look at some general properties of bases. Bases are electrolytic. They conduct electricity. Bases cause indicator dyes to change color, but they change it to a different color than what the acid changed it to. This gives us a way to tell if a substance is an acid or a base using this third substance called an indicator dye. If you were to taste a base, it would taste bitter. Again, don't test this because some bases are very dangerous when ingested, but the bases that are safe to eat, the bases that are put in food, for example, give it a bitter taste. Bases have a slippery feel. And bases, like acids, are caustic to body tissues. They will burn your skin. So what we've just discussed is acids and bases according to a scientist named Arrhenius, who said acids are substances that release hydrogen ions when they're dissolved in water. Bases are substances that release hydroxide ions when they're dissolved in water. Well, other scientists investigated acids and bases as well and came up with a different definition of when something is called an acid or a base. So the next definition we're going to look at is called the Bronsted-Lowry definition of acids and bases. In 1923, Danish scientist Johannes Bronsted and English scientist Thomas Lowry proposed the following explanation of acids and bases. Now this is going to be a little bit different than the Arrhenius definition. According to Bronsted and Lowry, an acid is a compound that is a hydrogen ion donor. A base is a compound that is a hydrogen ion acceptor. Why would we ever use this other definition of acids and bases? Why not just use the Arrhenius definition only? It seems really straightforward. If something makes hydrogen, it's an acid. If something makes hydroxide, it's a base. Well, other compounds have similar properties to those identified as Arrhenius acids and bases. You remember those properties up above? Acids are electrolytic. Acids cause indicators to turn a certain color. Acids taste sour, and so on. Well, what if there are other compounds that don't necessarily release hydrogen ions when dissolved in water, but they still have all these properties? Shouldn't we call them acids also? And that's what the Bronsted-Lowry definition attempts to explain, some of these other compounds that seem like they are acids or bases. Here is an example. NH3 aqueous plus water makes NH4 positive aqueous plus OH negative. On the left side of the arrow, there is not a compound that contains the OH ion, the hydroxide ion. But this first substance, NH3, which is called ammonia, has all of the properties of what Arrhenius would call a base. It's caustic. It has a slippery feel. If you tasted it, don't ever taste this, but if you did, it would have a bitter taste as you're then headed to the hospital. So we want to classify this as a base, even though it's not a base according to Arrhenius. This substance, NH3, is a base according to the Bronsted-Lowry definition. So let's take a look at that definition again. A base is a compound that is a hydrogen ion acceptor. Did this NH3 accept a hydrogen from the other substance that's a reactant to create a product that has an additional hydrogen in it? Well, yes, it does. NH4 positive has one more hydrogen than the NH3 had. So NH3 is a substance that is able to accept a hydrogen ion from a nearby substance. The NH3 is a Bronsted-Lowry base. It reacts with another reactant, in this case H2O, to produce a product. According to the Bronsted-Lowry definition, the substance that donates a hydrogen is called an acid. So H2O is functioning as an acid, according to the Bronsted-Lowry definition. Here is another example. HCl aqueous plus water makes H3O positive plus Cl negative. According to the Arrhenius definition, we would say that HCl is an acid because when it's in its aqueous form, it dissociates into hydrogen ions and chloride ions. We see the chloride ions explicitly listed here, and we've already discussed that instead of writing H plus aqueous, it's very common to write H3O positive aqueous. Does the Bronsted-Lowry definition of acids and bases fit? According to the definitions above, an acid is a compound that is a hydrogen ion donor. So does HCl donate a hydrogen ion to the other substance, which in this case is H2O, creating something that has one more hydrogen in it than H2O? Well, yes, it does. We can see that it makes H3O positive. That has one more hydrogen than H2O. So HCl is functioning as an acid. It's able to donate a hydrogen to the other reactant. And H2O is accepting that hydrogen, so it is a base according to the Bronsted-Lowry definition. So in the second example, we've identified HCl as an acid according to the Bronsted-Lowry definition, and that fits right along with the fact that we would have called it an acid with the Arrhenius definition as well. Here is a check for understanding question. An equation is shown below. Identify the acid and the base on the left side of the arrow. And then on the right side of the arrow, identify which substance is the conjugate base and which is the conjugate acid. The conjugate base is the thing that's created from the acid on the left side of the arrow. The conjugate acid is created from the base on the left side of the arrow. I'll pause the video for you to try this. Here's the solution. The HSO4 negative on the left side of the arrow is an acid. It's the substance that has a hydrogen ion that it can donate to the other reactant, which is the H2O. The H2O is the base. It's the substance that is going to accept a hydrogen from the HSO4 negative. Now on the other side of the arrow, you'll notice that the H3O positive formed from this base when it received that extra hydrogen. Now that it has an extra hydrogen, it could function as an acid because it might donate that extra hydrogen at some point in the future. This is the conjugate acid, meaning it's the acid that came from this base. Now let's look at the SO4 negative 2. This is called a conjugate base. It has no hydrogen in it, so it's definitely not able to donate hydrogens, but it is able to accept hydrogens if there were any nearby. So that makes it a base. It's a conjugate base, meaning it was created from the acid on the left side. You'll notice that these vocabulary words function in pairs. The original acid loses a hydrogen and turns into a conjugate base. The original base accepts an extra hydrogen and turns into a conjugate acid. If you reversed this reaction and you focused on the stuff over here as being reactants, then notice that this conjugate acid has an extra hydrogen that it could donate to the SO4, and it would create what you see over on the left side. All right, those last couple of examples were about acids and bases according to scientists named Bronsted and Lowry. Their definition involved transferring hydrogen ions. If a compound is able to donate a hydrogen ion to something else, then it's called an acid. And if a compound is able to accept a hydrogen from something else, it's called a base. There's a third definition of acids and bases. This third definition is the broadest definition of acids and bases. It encompasses the most compounds. It is the Lewis definition from the scientist Gilbert Lewis. He is the same scientist that we learned those Lewis dot structure drawings for molecules from. According to Lewis, an acid is a compound that accepts a pair of electrons. A base is a compound that donates a pair of electrons. You'll notice that the word hydrogen is not even mentioned here anymore. The reason for this additional definition of acids and bases is, again, because there was more substances that had those properties of acids and bases, like being slippery and being bitter and being sour and being caustic. And these other substances that have those properties didn't necessarily even have hydrogen in them. Here is an example. On the left side of the arrow, we have some reactants. You'll notice that neither reactant involves hydrogen, or for that matter, there's not an OH, a hydroxide either. There's a fluorine negative ion, and it's being combined with BF3, boron trifluoride. The fluorine negative ion is called a base, according to Lewis, so it's called a Lewis base. And the boron trifluoride is called an acid, according to Lewis, so therefore a Lewis acid. These combine together to make BF4 negative. You'll notice on the right side of the arrow, there's obviously nothing to do with hydrogen or anything over there. Now, the Lewis definition has to do with a compound accepting electrons or a compound donating electrons. So let's pay attention to the electrons. This particle right here that I circled in red has 8 electrons around it. This right here has a central atom, the boron, that only has 6 electrons by it, right? 2 electrons are in this bond, 2 are in this bond, 2 are in this bond. It has room for 2 more. In fact, that's pretty obvious because the left side of the capital B just has a blank spot. What's going on here is that when these two things get really close together, a bond can form. These 2 electrons can be donated to the boron. When I say donated, actually I kind of mean like shared with the boron. The boron accepts them. The Lewis definition of an acid is a compound that accepts a pair of electrons. Well, which one did that? The compound that had the capital B. It had room here on the left side to accept a pair of electrons. That's the one that's the acid. According to the Lewis definition of base, a base donates a pair of electrons. Well, which of the substances has 2 dots available that could sneak up right next to that capital B and kind of fill that position in? That's this one right here. These 2 dots, for example. So that one's the base. Here is a check for understanding question. Please identify which of the reactants is the Lewis acid. And then the other one would be the Lewis base. I'll pause the video for you to try this. And here's the answer. The Lewis acid has a place where it can receive a pair of electrons. Probably room right here on this side of the S. A Lewis base is able to donate a pair of electrons. Perhaps it's these 2 electrons. So imagine these get super close together and that these 2 electrons can get shared right on the left side of the S. Here are some summary observations. Arrhenius acids and bases are the quickest to identify because you're looking in the compound to see if there's a hydrogen in there. In that case, it is an acid, or if there's an OH, a hydroxide. In that case, it's a base. And not only that, but those are the ones that we focused on earlier this year, so you're used to those. Bronsted-Lowry acids and bases come in conjugate pairs. On the left side of the arrow, one of the things is an acid and the other one's a base. And then on the right side of the arrow, you can identify the conjugates for each of those. And a third observation, Lewis acids and bases can be identified from equations in which the Lewis dot structures replace the chemical formulas. That's why my example for finding a Lewis acid or base used the dot structure drawings instead of using just formulas like we did for the previous examples. In this chart are the 3 definitions and the key components of each definition. An Arrhenius acid is a compound that produces H+ ions. An Arrhenius base is a compound that produces hydroxide ions. A Bronsted-Lowry acid has a compound that is able to donate a hydrogen ion. A base is a compound that is able to accept a hydrogen ion. A Lewis acid doesn't have to have hydrogen in it. A Lewis acid is a compound that is able to accept an electron pair. It has to have some open spot in it where there's room for 2 electrons to go into that spot. A Lewis base is a compound that is an electron pair donor. It has to have some unshared pair of electrons on one side of it that is able to squeeze in close to something else so that those 2 electrons are being donated or shared to that other substance. This concludes the lesson about acid and base definitions.